All right, now this next section is called subgroups, which is based on a very simple idea that inside of groups can be other groups. Now this really does make sense. If you have a group, you have an operation, and that operation is defined on, so here let me just draw G, and I have an operation on G. So that operation is defined on any subset of G, and we already have inverses and identities. So as long as this subset contains all the inverses and identities that are necessary, then it seems like maybe we could find another group inside this group. One thing's for sure, that the identity of the group must be in any subgroup. Okay. We don't have to worry about associative property because the associative property works for any three elements in big G, so naturally it will work for any three elements in the smaller set. So that's just kind of a preview that subgroups are a cheap and easy way for finding new groups. Here's the definition of subgroup. A subgroup of a group is a subset. Now remember, subgroup and subset are not the same. There are plenty of subsets of a group. Most of the subsets of a group are not subgroups. These are different. Subgroup is not merely a subset. It has other conditions. Okay. All right, so it's a subset of the group with special properties. It's a subset such that when the group operation of the big group is restricted to the smaller set, then the smaller set is a group in its own right. Okay. All right, so let's see. So let's look at the even integers. Now remember, the integers form a group. The even integers, if you think about it, the sum of any two even integers is an even integer. Any even integer has an inverse that's an even integer. The identity is an even integer. So you could make an infinite addition table that only involves even integers. In fact, the even integers are a group in their own right, and they're contained in all integers, so they are a subgroup. Okay, so we just simply need to show that these are a group, and of course they are contained in the integers. Okay. Okay, so here's a proof going through the proof. This is similar to proofs that we've done before, so I don't need to do this in detail. Show that in fact the even integers have closure under the operation of plus. That's associative because even integers are integers, so they're associative by the associativity of plus. The identity is an even integer. Inverse of an even integer is an even integer. Okay. Okay, so here's some other operations. In fact, we have many subgroups of the group of integers. Okay, and there are also cases where subgroups are not, where subsets are not groups. Okay. Okay, so let's prove the. All right, so here we go. In fact, it's not necessary to start all over again. If you have a subset of a group, let me start that sentence again. If you have a subset H of a group G and you want to determine whether or not it's a subgroup, you don't have to go through all the group properties on this subset. Some group properties are inherited from the big group. In particular, as I mentioned a couple of times, that if the big group has an associative operation, then because the subset uses the same operation, it's automatically true that this subset with the same operation will be associative. So in order to show that a subset is a subgroup, there are only three things you need to guarantee. First of all, you need to guarantee that the identity is in this subset. You need to show that if there are any two elements in the subset, then their product is in the subset. And you also need to show that if an element is in the subset, then its inverse is in the subset. All right, so here we do some more examples of subgroups. And I think that's pretty much the end of this section. Oh, no, here's a little more. All right, here's a simplified version of those three conditions. In fact, all you need to show that a subset is a subgroup if it's a non-empty set, and if it's always true for any two elements in the set that G and H. If G and H are in H, then GH inverse is in H. In fact, from this one condition, you can derive the three conditions that were given here. From that one condition, you can derive A, B, and C. Okay. So you can read this proof and see why that's true. Okay, more exercises. And here we're going to talk about another special type of group, so I'm going to stop here.